So the next topic is an important consequence of, not a consequence, a method of proving that something is countable. You have examples of things that are countable. You have examples of things that are uncountable, but there must be a better way of proving it for difficult things, right? So proving countability in many ways. But in my opinion, at least in this context, the most powerful tool is the following theorem. I don't know who came up with this theorem. Let's just say this is like folklore or something. So if you take any finite amount of finite sets and you put them all together, so the finite union meaning you take a finite amount of finite sets, right? The finite union of finite sets is finite. And I don't have to prove this. You prove this in the tutorial. If you have two sets and they both are finite and you take the union, you get something that is finite. Inductively, this will apply to any finite number of finite sets, right? So we don't need to do that. Similarly, the countable union of countable sets is countable. Now, this is not difficult to prove, but I do want to highlight something in the hopes that you appreciate that this result is still interesting in of itself for the following reason. So here's a question for you. There's more than one way of interpreting this, right? But finite means less or fewer than aleph naught, because I already said aleph naught is the smallest infinity. So anything smaller than it must be finite. So the first thing, the fewer, the sum or the union, right? The sum is the union. The sum of fewer. Okay, so let me rewrite this. In other words, I want to write this in a more set theoretic context or language. The sum of fewer than aleph 0 sets of size, of finite size, meaning of size less than aleph 0. Why am I writing this in such a contrived way? Just because I want to make a point, right? You don't have to follow this this thread in this way. And how would you express the same thing with countable? Well, countable means fewer than the smallest uncountable cardinal, right? If that makes sense. So the sum of fewer than here it wouldn't be aleph 0, but the first one that comes afterwards, which is aleph 1, right? So the question is the sum the same thing, right? Same thing, sum of fewer than, and this time I will just pick this cardinal, which is the reals. Is it the same conclusion? By the way, I just noticed I didn't write the conclusion. So I need to shift this entire thing down. Okay, I hope this makes sense. If it doesn't, please let me know. This is just to make a point, right? This is not really part of the theorem that I'm going to write down. I'm going to prove. Okay. So the sum of fewer than aleph 0 sets of size less than aleph 0 is less than aleph 0. It's finite. It's still finite. Take finitely many things, and each of them is finite. Add them up, you get something finite. And the same conclusion appears for aleph 1. So my question is if the same conclusion appears for R. And the answer is that this is also undecidable. But it is way more difficult than the previous thing. This is also undecidable. In case you're interested in this sort of thing, the only takeaway from what I'm writing down, the only surprise you should take home about this is that these questions are difficult, right? Even if the proofs, some of them are not too complicated, they are not too far away from the unknown or things that are literally unknowable. So, so this is why I find this interesting. So let's prove the theorem. Let's prove the theorem, right? This theorem. How do you prove that the countable union of countable sets is countable? Proof. And let's try to be a bit more formal this time. I haven't really done many formal proofs today, so let's do this. Assume that F is a family of countable sets. Now, I could just say pick a function and this and that, but of course, we already know that this means that there's a sequence, right? So countable means that F is, let's enumerate it in order type the natural numbers. Maybe let's use n as an index, so why not? Doesn't matter, right? So we can definitely do this, where each an is countable. So, okay, I have a question in the chat. Okay, so this is a good question. This is a good question. So the question in the chat is, what does sum mean? Okay, sum means it's either finite sets, in which case I'm adding up natural numbers. I'm adding up 5, 7, and 9. Or sum means the cardinality of the disjoint union. So it's the same situation that happened in the clarification before. Either 2 to the n makes sense as a number, or I'm defining it that way because I have no other way of making sense of that symbol. Same thing happens here. Either the sum makes sense as a sum of natural numbers, or I am defining it as the cardinality of the union. So I could have defined all of these operations on cardinals, but we don't really use them outside this context. But that's a really good question. So maybe I can add a small comment, and hopefully this is clear. And let me read the second part of the question. Does this mean every set in the sum size less than Aleph naught, or the amount of sets we're summing up less than Aleph naught? Both, right? The amount of sets you're adding up is less than Aleph naught, and each set has size less than Aleph naught, right? So in this case, sum means just a sum of naturals because all of these will be finite, right? So this is the usual sum. And here, when I'm talking about bigger sets, well, this will be the size of the disjoint union. Right? It matches what you would expect would happen for finite sets. So for infinite sets, we just define it that way, right? How do you add up to cardinals? So maybe I can clarify this. A plus B, when A and B are possibly infinite, it's just the size of A union B, disjoint set. So like I said, this whole part in other words is just a comment, right? This is not really part of the lecture, and it's not too crucial. It could be more than two sets. It could be more than two sets. In which case, the union would be something bigger, right? So I'm sorry, this is a bit messy now, but it could be more than two sets. So this is defined as the set, the size of this of this, right? So if you're adding up more than two, then that makes sense. It either makes sense as natural numbers or it doesn't. And in that case, you're defining it this way because there's no other way to define it. How do you add up Aleph naught with some other number? Well, you define it this way. This is the definition. And the definition makes sense because it is consistent for finite sets. And that's what you proved in the tutorial. But understanding the notation is not that important. We won't ever use that notation again. Do let me know if this is confusing in the problem set, and I can change the notation so that it doesn't even talk about cardinals, right? We haven't really explicitly talked about cardinals other than using them for this context. Finitely many sets would be the first case, yes, finitely many sets, in which case it's just a normal sum. For the subsequent ones, it could be a bigger sum, right? You could be adding up infinitely many sets. How does that make sense? Well, it doesn't. That's what the symbol means. Yes, of course. And if something is still unclear about this, feel free to post this on Piazza, and I will try to clarify it. Or even I can even remove the notation that might be a bit cumbersome to read. There's nothing deep about this. That's, I think, the most important thing about this last thing that I'm clarifying for Bill here. There's nothing deep about this. It's either a definition or something that we can easily prove for finite sets in terms of the notation. Let's prove something that is not trivial, however. So recall what I'm trying to do is proving that the countable union of countable sets is still countable. And this isn't obvious at all because countable could include infinite, right? So if you have infinitely many slices of infinite pi and you glue it all together, how is it obvious that the pi you have might still be the same size as any slice that you started with, right? That's maybe a weird way of saying this, but okay. You have a countable family of countable sets, so let's enumerate this countable family as an, and each an is countable. So there is an injective function f, and let's put an index on the injective function so that it's easier to keep track of what is what, from a to n. That's what it means to be countable, right? Now, I'm already using the injective function for f to enumerate this an, but I think that step is clear. Let me know if it's not. So any questions so far? All I've done is say, okay, f is a countable family, so I've listed out as an. Each an is countable, so there must be some injection that enumerates an, right? This isn't really that deep either. So here's a0, here's a1, here's a2, and this list is infinite, right? It goes on forever. It's infinite, but still countable. That's the point. So a0 has a bunch of elements. It has an a0, a1, a2, a3, a4, and so on. A1 also has a bunch of elements, so we need to come up with a better way of labeling them. So let's put, I don't know, let's put a hat on all of these with a 0, right? So that everyone knows where they're coming from. This isn't different from the Hilbert's Hotel. Each row is a bus of people, and the columns are in listing out all the buses, right? So the second bus, everyone gets a tag with the number 1 so that they remember which bus they came in. And this is A1, A2, the second person in the first bus, sorry, the second person of the second bus, fourth person of the second bus, and so on, right? So down here, you will have a person that's the first person of the nth bus. This is a matrix, right? It's just a matrix. You have 2 parameters to denote anyone. You can find anyone by knowing what bus they're at and what seat they have. This is the idea. So why should this set be countable? Well, we need to find a way to make a list of all of these people. In other words, we need to fit all of these buses, all of these people, into Hilbert's Hotel, which only has 1 room per natural number. So the first natural number will be the first person, the first bus. The second one could be this one, and then this one, and then we can go in a sort of zigzag way, right? That's one way of listing them. We have a better way of doing that. That's easier to write down, maybe not as easy to draw the way I'm doing it now. So how do we list them? That's the goal, right? We need to show that this family, the union of all of these together, is still countable, even though this could be many sets, right? Now, why is this so similar to Hilbert's Hotel? Let me remind you what we did with Hilbert's Hotel. Hopefully I can find it quickly. So this is Hilbert's Hotel. It's the same idea. It's the buses and the people, and I need to squeeze them all into these room numbers, right? Here, we are proving something different. We are proving that n cross n is the same size as n. Why is this so similar? Doesn't it feel like it's the same idea, only slightly weirder or slightly written slightly in a different way? So if you want to hopefully not get confused with this, here's one way you can think about this. What is the size of the union of all of these AIs, or all of these ANs? This is the set we want to prove is countable. This is an informal argument. I just want to show you that this isn't that deep either. So I am adding up each individual size. Now, what does this sum mean? It's just a symbol, right? It's just the symbol I use to denote the size on the left. So this equal sign is by definition. I haven't really done anything, but intuitively, this is what I'm doing. This is what is happening. So if each of these sets has size at most n, and this is an informal argument. I haven't proved that you can do this with cardinal numbers, but this should make sense to you in that these are numbers after all, right? So they should behave in a way that is not too weird. So each summand, each part of the sum is at most size aleph naught, right? So this is just aleph naught. And there we go. Now, how many parts, how many pieces, how many factors do I have in the sum? Well, the sum is iterating over the natural numbers, so shouldn't this just be aleph naught times aleph naught? And in the previous lecture, we proved that this is just trivialized equal to aleph naught. Multiplying two infinities together doesn't make it bigger, right? I haven't done anything. This is not an argument. This is just a way for me to convince you in a hand-wavy way that what we're doing makes sense, right? If these numbers, these cardinals, behaved like numbers, then this should happen, right? Like this, I should be able to do this step or something very similar. So hopefully this helps you gain some intuition, some insight as to why are these two arguments with the buses and the people so similar? I'm trying to cram in every person on every bus into a room. Now there are some differences I should confess in the argument. For example, this person that is in a red circle, A0, 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 0, I don't know if it's different from this number right here, right? I didn't say if the sets are disjoint or anything like that. So that's something I have to keep in mind. These could be the same people, the same person, just for some reason sitting in two different buses at the same time. So the analogy isn't perfect. There's another thing that could happen, which may make things complicated. A2 could be empty. Why not? There's nowhere that says that countable needs to be non-empty or infinite or anything like that, right? So if A2 is empty, well, that's going to complicate things when I write it down. Let's write down the formal argument, and then I will give you time to absorb this. And then we can maybe look at some easy consequences of this. Feel free to use this theorem in the problem set. It is useful for some things. You can, for example, use it to prove this thing in the first place, which is, I think, part of your problem set. And it is an easier proof. Okay, so I think I've been talking too long. Let's just do the proof and see if we can make sense of it. So how do we make a list? How do we make a list? We need to define f, a function that goes from the union, which may or not be disjoint, of all of these sets into n. We want an injective function, right? So how do we do this? How do we list out all of these sets? There's many ways we can do this, right? We can zigzag, we can pick something, I don't know. There's more than one way of doing this. Any element x inside this set is in some an. That's the definition of union, right? If something is in the union, it has to be in one of the pieces. So it is in some n. So we can either pick any index that you want, but since these are natural numbers, then why not pick the smallest one? So let n sub x be the smallest, right? Remember that we saw any non-empty set of natural numbers has the smallest element, right? A minimum element. This is the well-ordering principle. We don't need it here, but this is, I think it's cleaner to write it this way. nx be the smallest index, such that x is in a nx. So up here, what would be n sub x when x is this fellow right here, right? So we said that that person could be the same as a00. In that case, nx would be 0, even though they could appear in many buses at the same time, right? If you don't like this, if you feel the analogy breaks down too much, if people are allowed to be in more than one bus at the same time, well, then just assume that the sets are disjoint. I don't want to do that because it will weaken the theorem, but if it makes this easier to write down, easier to sketch out, then feel free to do so. So any element x is in some an, so let's call nx the smallest index. And now all we have to do is the following thing, right? How do I define f of x? X is the input, so any arbitrary element of the union. Where do I send it to? Where do I send x, the person, the nth person on the mth bus? Where do I send them to? What room number should they get? I don't need a bijection, by the way. I just need any way that doesn't repeat people. I don't want more than one person in the room, in the hotel room. Let me go back and maybe I can find inspiration. I can find inspiration from the previous idea because, like I said, these two ideas are equivalent, right? They're describing the same phenomenon about cardinals. So any ideas? Any ideas? I will let you look at this solution that we saw last time for maybe a minute, and then we can go to this one. Also, if something doesn't make sense, then let me know. If something is unclear about the statement, okay, so let me go back to the current lecture. So what should I write here? What should be the room number of x? We already know what bus x is on. X is on the n sub x bus. And we can also figure out what place they occupy in that bus because we have an injective function, which is f. Fn tells me what position they occupy inside the bus. Maybe they occupy no position, right? That's not really a problem. Actually, now that I think about it, it might be a problem. Can it be a problem? No, it cannot be a problem. I can only pick people that are in non-empty buses, obviously, right? So yeah, never mind. Feel free to just unmute yourself and say the first thing that comes into your mind. What can we do here? Think about this as a form of bookkeeping, right? There's a receptionist in the hotel, and they're trying to figure out where to send each person. And each person comes with two pieces of information: the bus they're on and the seat that they were on that bus. So using those two pieces of information, what room number should they get so that no two people get the same room number? Any ideas? If you believe what I said last time, then there's actually an easier way of doing this, right? Okay, so Yi Yang, I see a suggestion in the chat, which is the product of powers of primes. So indeed, all we have to do is do something like this, right? So 2 to some number, and that number can indicate the bus, the bus, the bus that they're on. And the second number, let's pick maybe something different. Should we pick a different prime just to add some variety? 5 to the 7. And what seat were they on? Well, we just have to ask the injection. Now, here's an interesting comment. This may not be a function since the sets may not be disjoint. Okay, but this isn't problematic because I'm only picking one index at a time. So you are right that if the sets are not disjoint, this is complicated, right? Someone gets to the hotel and says, I'm on buses 13, 45, and 117. But the receptionist only has to listen to the first bus that they came on. They can ignore the rest of the buses, and if they only pick one at a time, this is unambiguous what room number they would be sent to. So we don't need the well-ordering principle, but it makes it easier for the reason that you just described in the chat. The fact that this may not be a function. It is a function if I pick an index, just one. But this is a very good observation. This is a very good observation. I can't just pick an arbitrary, not all indices, right? Because then you're right, this would not be a function. The same person would get a different room for every bus that they were on. That's not what we want. And that's not what happens in this case. Now, okay, maybe I can just add one final thing. So F is injective. By the fundamental theorem of arithmetic. For the same reason that we did it last time. And we could use the previous result to prove this as well. Because instead of sending this to 5 to the nx, 7 to the fnxx, I could just send it to a tuple, to the pair nx and fnxx, right? If I just pick the pair without just ignoring the prime numbers, this defines an injection from the union to n cross n, which I already know is countable. But this is a more pure way of writing it, right? I don't need any other result for this except the theorem. Okay, I'm going to add a square because I'm done with the proof, but I do want you to tell me if there are any questions, any sort of ambiguity from this. Please let me know. In the meantime, I can write some interesting consequences about this. I mean, I could use this for many different things, but right now let's just focus on some interesting examples. If you take the set of all finite tuples of the natural numbers, or any countable set, because of course it won't matter, this set is also countable. So how do you do that? Let me know if you have any ideas or questions about the theorem. It may take you time to reread this. By the way, Yi Yang, are you convinced that this is in fact a function, or do you not think this is correct? Okay, great. Okay, so the set of finite tuples of n is countable. And this isn't that easy to prove without the result that I just wrote down. It's not that easy, right? But with the result, it's not hard. So for any n natural number, if you take the n tuples of n, right? This is the n tuples. So this is the set or n sequences, if you want, the set of n tuples equivalently n sequences of length n, right? Sequences is countable. Why? You can either use induction on the fact that n cross n is countable, because this is just n cross n cross n cross n times, right? So either use induction on n cross n cross, n times in total. Or you can just prove this directly, right? You can just define f from n to n, and you can do the same trick we've been doing all this time, right? Just a1, a2, this is a tuple or a sequence, right? So you can list it and just send this to 2 to the a1. The powers of prime trick. This one works for any number of finite things, right? Not just 2. There's a reason why we have so many primes. I mean, in as far as the usefulness goes, right? This is a prime, the nth prime. And a to the n. This is injective. This is at least two very different ways of proving that n to the lowercase n is countable. Countable. So write this as exercise. How do you write exercise? Exercise. Right? But we're not done yet. Because now the set of all finite tuples, right? Not just the tuples of size 3 or 4 or 5, but all of them together. What is the set of all finite tuples? Well, a finite tuple has either size 0 or size 1 or 2 or 3, but it has to be some element of this union. And if each part is countable, then the union is countable by the theorem, right? So notice that this isn't actually that easy to prove without the theorem. How do you prove that if you take any length, any acceptable length, and all of those finite lengths together, that your set is still countable? This isn't obvious. And you will use this in the next problem set for the topology on the reals, if I am not mistaken. Or actually, I think you are using this for this problem set, right? Something about Cauchy sequences. Sorry, I get the two problem sets mixed up because some of them have different, similar ideas. Any questions about this? Does this make sense? This is a good exercise, by the way. If you're struggling, or not struggling, but if you want to understand the context a little better and appreciate why this is useful, then I recommend you try writing this. Just rewrite the proof I just have here in your own words, and hopefully it will become clear. The same trick applies for the set of all finite sets. The power set is always bigger, but those subsets that are finite are never bigger for an infinite set. It's always the same amount, which is interesting. Okay, so here's a question. What is the union of all finite tuples? Do they necessarily have the same dimension? No, here they have all possible dimensions. So the set of all finite sequences of natural numbers is countable. The set of all sequence in general is of course uncountable. Just the binary sequences are already uncountable. But if you limit the size of the sequences, you get a countable set. This is how you build intuition. This is how you build intuition, right? So here's the argument. This is the takeaway. So this is how, okay, let me write this as a comment to draw your attention to this fact. So notice 2 to the n is uncountable, right? So just the set of all sequences of zeros and ones is already way more than the natural numbers. But all possible sequences of natural numbers, if you limit the size, that's still countable, right? But this is countable. So this is perhaps not that intuitive. So the difference between countable and uncountable, whether you can list something or not, has to do with the size of the objects that you're using to construct things, right? Think about it this way. How do you describe an object here? you need infinite information to capture that object, right? You need an infinite list because if you stop at any point, you don't know what's going to happen after that point with the zeros and ones. But with this, you can always stop after a very long time, but always a finite amount of time. And if you stop, you will have read the entire sequence because all these sequences are finite. The thing that is weird, in my opinion, or that I want to draw your attention to, is that this set contains sequences of arbitrary size. So there's infinitely many possible sizes there, even though all the sizes are finite. And this set is still countable, even though the one on the left is not. Now, I know this is the first time many of you are seeing this topic, so I do suggest you look at the recording again, give this a read, try the exercises, and whatever is confusing about this, whatever is unclear, please let me know. Also, my connection might be a little bit unstable, so I think the recording will be better in case you want to rewatch it. There's one more example I want to write, which is important. A number, a real number, is called algebraic. Question in the chat, let me see. Okay, it doesn't sound hard to prove as naturals can have arbitrary length in base 10 as well. Yes, that is true. But so the difference here is sort of what requires more information to be captured. And infinite binary sequences, there's a lot more of them than there are of finite sequences. So yes, I agree. I agree that you can build intuition on this, but maybe the first time you see this, it's a bit surprising. So a real number is called algebraic if it is the root of a polynomial of an integer polynomial. What does that mean? X is algebraic if and only if there are n, a natural number, and then the coefficients, right? A1, an integers, such that if you take the polynomial with these coefficients from 0, I should start with 0, I think, standard, and you apply to x, then you get 0, right? So what are we will not cover this in detail, of course, but if you want examples, so any rational number is algebraic p over q because p over q is the root of what? So if I take p minus qx as a polynomial, that one has integer coefficients. P and q are integers. And if I plug this rational into that, it gets 0, right? Is a polynomial. So every nomial, sorry about that. Any rational number is algebraic, but there's many more, right? We discussed root 2 being not rational, but it is algebraic. It is algebraic. Why? Because x squared minus 2 is a polynomial whose root is square root of 2. There should be a power. Oh, yes, thank you. There should be a power. Yes, thank you. So there should be an I on top of x. Yes, thank you, Max. Okay. So root 2 is algebraic. The nth root of any prime number is algebraic. And if you continue doing this, we didn't study this theory in this course, but there's a lot of things that you can do, right? The algebraic numbers form a sort of field in which you can keep taking roots and you can add them, multiply them. Most numbers you have ever written down in your life are algebraic. The only algebraic numbers you don't, the only numbers you may know are not algebraic are pi and what else? Maybe e, right? The number e, the base of the exponential function. And for most people, I think that's the only one you can name. And I myself cannot name more than 5. Actually, I don't know if I can name more than those two. I mean, there's others. Anyway, most numbers you will ever think of and deal with are algebraic. But the set of algebraic numbers is of course countable because okay, something's happening to my pen. The set of algebraic numbers is countable because I only need finitely many parameters out of a countable set to define them. So maybe I have to leave this as an exercise because I don't want to restart my computer right now. Okay, I made it almost to the end this time. Yeah, okay, I cannot write anymore, but the thing that was missing is the set of algebraic numbers is countable. How do you prove this? We can either write this down next class, or let's write this as an exercise. It's not difficult, especially the way I wrote the definition at the top. You just have to take the union over n, the union over a0, the union over a1, and so on, all the way to an. This is only finitely many parameters, so it's fine, right? So this time you don't just have one union, you have an arbitrary but finite amount of unions, but each thing inside the union will be countable. So the union over all of them is still countable. Why is this surprising? Because it means that most real numbers, given that they are not countable, most real numbers are not algebraic. Almost all the real numbers are not algebraic, even though you cannot name more than 2. And you can name infinitely many rational numbers, algebraic numbers, stuff like that, right? So this, I find this very surprising. Okay, I will stay here for the next 7 minutes. Should you have questions, we stop the recording.